So now we're going to learn about buffers. Buffers is defined as a solution characterized by the ability to resist changes in pH when limited amounts of acid or base are added to it. Buffers work in pairs, kind of like how your shoes are in pairs. You have a right shoe and you have a left shoe. For buffers, you have a weak acid and its conjugate base, or a weak base and its conjugate acid. So let's do a problem with buffers, and we're going to do an ice table. A buffered solution contains 0.5 molar acetic acid and 0.5 molar sodium acetate. Calculate the pH of this solution. And remember, sodium is a spectator ion, so we're going to ignore the sodium. So let's start by filling in your initial. Acetic acid, 0.50. Acetate, 0.50. Then we'll do our change. Minus x plus x plus x, and then our equilibrium. 0.50 minus x, 0.50 plus x. So now we have our ice table. We can use it as our directions. And we can solve for pH. This is acetic acid. It has a Ka of 1.7 times 10 to the minus 5. That's going to be equal to x times 0.50 plus x over 0.50 minus x. So we get all of that from our equilibrium row on our ice table. We're going to use the 5% rule to simplify. So we get x times 0.50 over 0.50. Of course, 0.50 and 0.50 cancels, so our x is 1.7 times 10 to the minus 5. Now, if you go back to the ice table, x was our concentration of hydrogen ion. So we put that into our pH equation and solve for pH. So make sure that you can do that on a piece of scratch paper. Use 1.7 times 10 to the minus 5 for your hydrogen ion. And then make sure that when you solve for the pH that you get 4.76955. Don't worry about all those digits. I got kind of crazy. Okay, so let's look at another problem. Calculate the change in pH when 0.01 mole of solid sodium hydroxide is added to 1 liter of the buffered solution in question 3. Compare this pH change with the change that occurs when 0.01 molar of solid sodium hydroxide is added to water. This sounds complicated, but it isn't. We get to use an ice table, but before we do that, we have to use what I like to call a stoichiometry table. So we set up our reaction. Acetic acid plus hydroxide goes to acetate plus water. We fill in our initial. Acetic acid was 0.50. That was from question 3. Acetate was 0.50, also from question 3. Because this is a 1 liter container, the hydroxide is 0.010 molar. And notice that we're just not even showing the sodium at all. Sodium is a spectator ion, so we won't bother with it. So now you get to use the skills you learned in Chemistry 111A. This is a limiting reagent problem. Hydroxide is your limiting reagent. So you're going to subtract 0.010 from the acetic acid, 0.010 from the hydroxide, and you're going to gain acetate, 0.010. You're reacting the acetic acid with the hydroxide, and you're gaining product. When you do your math, and so your final molarity is 0.49 for the acetic acid, 0 for the hydroxide, it got all used up, 0.51 for the acetate. Now that you have done your stoichiometry table, you can do your ice table. So your initial for acetic acid is 0.49. Your initial for hydrogen ion is 0. Your initial for acetate is 0.51. You got all of those from your stoichiometry table, final molarity. The change is minus x plus x plus x. Your equilibrium is 0.49 minus x, and 0.51 plus x. So now you're going to sub your Ka. Remember, the Ka is the products over the reactants. In this case, our Ka equals x times 0.51 plus x on the top, 0.49 minus x on the bottom. We're going to use the 5% rule. And so we get x times 0.51 over 0.49. And that equals our Ka of acetic acid, which, as you recall, we go back in our previous table, our Ka of acetic acid was 1.7 times 10 to the minus 5. So that's the Ka value you would have put in here, where it simply says Ka. You solve for x, and you get 1.63 times 10 to the minus 5. That is your hydrogen ion concentration. You plug that into your pH equation, you're going to get a pH of 4.79 for this buffered solution. That means when you added the base to your buffer solution, the pH was 4.79. Now, what would happen if you added that amount of base to water? If you look at the bottom, you'll see 0.010 mole of NaOH over 1 liter. That's 0.01 molar NaOH. You would calculate your POH to get 2. And then remember, POH plus pH equals 14. So you would get pH of 12 if you added the same amount of sodium hydroxide to water. Now, if we compare these, we can see that the pH of the water is very basic, whereas the pH of the buffered solution did not change very much at all. So that means the buffered solution is working. Okay, onward. One of my favorite equations of all time, the Henderson-Hasselbalch equation. I like to call this the HH equation. pH equals pKa plus log of the conjugate base on top over the acid on the bottom. Now you calculate pKa the same way you would calculate a pH. You would put the value in for the Ka and get a pKa. So pKa equals minus the log of the value of the Ka. So our first question is, what is the pH of a solution containing 0.05 molar acetic acid and 0.3 molar sodium acetate? So again, sodium is a spectator ion. We set up our HH equation. We get pH equals pKa plus log. On top is acetate, on bottom is acetic acid. So our pH is 4.77 plus log of 0.30 on top over 0.05 on the bottom. We get a pH of 5.548. So what you should do is you should practice this and check and make sure that you get the proper pH. Remember, this is acetic acid solution, so we're using the same Ka value as we used in the prior problem, but we're solving for pKa. Those of you who are going to take OChem in the fall, please be very good at understanding pKa, because some of your professors are, well, all of your OChem professors are going to talk about pKa values rather than Ka. Okay, so let's look at a problem. Above our solution contains 0.25 molar ammonia. It has a Kb of 1.8 times 10 to the minus 5 and 0.40 molar ammonium chloride. Calculate the pH of this solution. First, use a table, then verify with the HH equation. So ammonia is a weak base. The lone pair on the ammonia is going to grab one of the hydrogens, and that will give you the ammonium ion. So in this case, we've got 0.25 molar ammonia, so fill that in on your ice table for initial. And from the ammonium chloride, we have 0.40 molar ammonium ion. Chloride is a spectator ion, so please fill that in on your ice table. And initially, we have 0 hydroxide, so we put 0. Our change is minus x plus x plus x. Our equilibrium is 0.25 minus x for our ammonia, 0.40 plus x for ammonium ion, and x for hydroxide. Now we have to remember that ammonia is acting as a base. That means we need to use a Kb. So our Kb for ammonia is 1.8 times 10 to the minus 5. That's going to equal products over reactants. And we'll plug in from our ice table. So go ahead and write that part down. Then we're going to use the 5% rule. We're going to simplify. So we're going to get 1.8 times 10 to the minus 5 equals 0.40 times x over 0.25. Our x equals 1.125 times 10 to the minus 5. From our ice table, we see that that is our hydroxide concentration. So our pH is 9.05. So now let's use the Henderson-Hasselbalch equation instead. Okay, it looks like I'm just writing crazy all over here, but don't panic. Oh, go back. So our pOH was 4.95. Put that into our equation, pOH plus pH equals Kw. So you guys know how to do that. You got the pOH, you get the pH, 9.05. Now we'll use the Henderson-Hasselbalch equation instead. Okay, this is a base. Remember, Ka times Kb equals 1.0 times 10 to the minus 14. We were using ammonia in our reaction here. So we're going to use the Kb of ammonia, 1.8 times 10 to the minus 5, to solve for the Ka of ammonium ion. We want the Ka of ammonium ion because we've been using pKa for our HTH equation. I don't want to complicate matters. The smart people can do different ways, but let's just, us normal people, do it this way. So we solve for Ka of ammonium ion. We get 5.56 times 10 minus 10. We can take that and get our pKa. And then now, since we have our pKa, we can use the Henderson-Hasselbalch equation. pH equals pKa plus log. In this case, our acid is ammonium ion. Remember, the acid goes on the bottom for our Henderson-Hasselbalch equation. And the top is our base, NH3. So we plug in our values. We get 9.255 plus log. On top is 0.25. On the bottom is 0.40. So you're going to want to practice that with your calculator. You get a pH of 9.05. They had better match, and they do. So when I do these questions, if someone doesn't force me to use the ice table, I just go straight to the Henderson-Hasselbalch equation and use that. So unless you are specifically asked to do ice table, feel free to go ahead and use the Henderson-Hasselbalch equation. Okay, another buffer question. Calculate the pH of the buffered solution in number 3 if 0.1 mole of gaseous HCl, which is hydrogen chloride, is added to 1 liter of it. So this is all part of the same problem. So let's fill in our initial. Ammonia is 0.25. The hydrogen ion is from our hydrogen chloride dissolving in water and giving hydrochloric acid, which is a strong acid which dissociates to give you the 0.1 molar hydrogen ion. Our ammonium from the previous question was 0.40. Another limiting reagent problem. So our change is minus 0.10, minus 0.10, and plus 0.10. So we get a final molarity of ammonia 0.15, a final molarity of ammonium ion is 0.50. We put that into our Henderson-Hasselbalch equation. Remember, ammonium is the acid, so that's on the bottom. Ammonia is the base, so that's on top. So our pH is 9.255 plus log. On top is 0.15, on the bottom is 0.5. We get a pH of 8.73. So it makes sense that this is still basic because it's ammonia, and ammonia is a base. So let's look at another type of buffer question. A chemist needs to prepare a solution buffered at pH 4.0. Which of the following systems will work best? So you're given all these Ka values, and you would have to calculate pKa, but I've done it for you. So when you get a chance, you're going to want to take these Ka values, and you're going to want to practice calculating the pKa. So go ahead and write those down, and then in your spare time, you can practice. So the step one would be to calculate the pKa values of each acid. And then this one, you use the acid with the pKa value closest to the pH of the desired buffer solution. So 4.1938 is closest to 4.3, so we will want to use benzoic acid. That's it. That's all you do. Okay, well, that's it for buffers.